Hey guys, so in this video I want to go over some more difficult proofs and get some practice with some of the inference rules that we covered towards the end of Unit 3, as well as get an example of conditional proof. So hopefully this will give some illustration to some of the concepts that we covered in the text. Alright, so let's take a look at this first proof. As you can see, there's a little bit more complexity in the individual statements, so we have three premises and one conclusion. So if you like, you can take a moment to try and see if you can come up with a solution for this on your own. But before we dive into it, first thing we need to do is just get the premises into the proof. So let me just go ahead and do that. Okay, premise 1. Second premise, and third premise. Okay, so let's take a moment and think about this. So we're trying to get to S or K. It's a bit of a weird proof. We have S or T to start, so that's kind of close to where we're going. Here we have a conditional. Actually, the antecedent of this is S or T, which is exactly the same statement here. So that brings to mind modus ponens is maybe a good way to start. And then here we also have a second conditional. And what do we notice about this? Well, we have two conditionals here, and there's a parallel insofar as the consequent of this conditional is identical to the antecedent of this conditional. So that's a good opportunity to apply hypothetical syllogism. Right, so those are the kinds of things that I'd be thinking about when I approach this proof. Here I've got a disjunction, and that might be an opportunity for a disjunctive syllogism, but I'm not seeing, for instance, not S or not T at this point, so I'm not going to be able to do much with that. So probably the most direct way to start would either be with modus ponens, using this statement and this statement, or to apply hypothetical syllogism. So let's go with the second option. So hypothetical syllogism is when you have two conditionals and the consequent of one is identical to the antecedent of the other. Then you can kind of cancel out that common chain link and directly connect the antecedent of the first to the consequent of the second. Okay, so this part is the same, so I just kind of cancel that out, and I go from this statement directly to this statement. So that would look like this. Hypothetical syllogism 1 and 2. Okay, so what can I do from here? Well, the most obvious thing would be applying modus ponens. Right, here again I have a conditional, and I have independently asserted the antecedent of the conditional, which exists on its own line. So I get to apply modus ponens and infer the consequent of the conditional. So I get T implies K. And again, the rule for that is modus ponens 3 and 4. Okay, now I've got T implies K. So now what do I do? Let's look again at the argument that we've got here. Now, one thing that I notice is I have already S or T. I'm trying to get to S or K. So I can think about this like I have two options. On the one hand, I have S. If S is the case, then obviously S is the case. So if the left-hand side holds, then the left-hand side is also going to be true for this statement. So what about the right-hand side? Well, what if T is true? Well, here I'm told T implies K. So if T is true, then K is going to be true. So I can see how these things are kind of connecting. And there's a couple ways that I could proceed here. So what can I do to get what I'm looking for? So let's see. So that the reasoning that I just talked about might be thought of as kind of a constructive dilemma, right? Where you have P or Q, and then you have, say, P implies R and Q implies S. So then you end up with R or S. That's one strategy that we can try to pursue, but I'm going to try a different approach here just to illustrate some other concepts. So one thing that I really want to, that I want you guys to get familiar with is converting between a conditional statement and a disjunction. So conditionals are equivalent to disjunctions. I'll just try to illustrate how so. So if you have a statement like P implies Q, that's going to be equivalent to not P or Q. And the rule that lets us do that is known as material implication. And that's a rule of equivalence, which means that it can go in either direction, meaning from this form to this form, from a disjunction to a conditional, or from a conditional to a disjunction. And also it can be applied to subformulas. So if you're getting stuck on a proof and you are have a bunch of conditional statements and not sure what to do with it, or you have a disjunction, just remember that you can translate between disjunctions and conditionals, and this is definitely a really useful tool in a lot of proofs. So let's see how we can apply that here. So here I've got S or T. So how can I turn that into a conditional? Well, remember from material implication, if you have a disjunction like this, then you form a conditional by taking the negation of the left-hand side, right? And the consequent becomes the right-hand side on its own. So I would take the negation of the left-hand side, which in this case would be not S, and then I would leave the right-hand side the same. Okay, so in the end I go from S or T to not S implies T. Okay, that's perfectly valid inference. And again, the rule for that is material implication. Let's just call it like this. On line 3. Okay, so how does this help? Well, let's take stock now. So here I've got T implies K. Here I've got not S implies T. So again, two conditional statements. They have a common link. Okay, the T is the same here, the antecedent of one and the consequent of another. So I'm going to directly link the antecedent of this statement with the consequent of that statement. Not S implies K. And again, that's hypothetical syllogism. This time lines 5 and 6. Okay, now what? So how can I get from here to my goal? Well, remember what I was just talking about a moment ago, that conditionals and disjunctions are sort of translatable. So how would we turn this statement into a disjunction? Well, remember, you take the antecedent, the left-hand side, and you take the negation of that. So here we have not S, so we're going to negate that. It becomes not S, and then you leave the right-hand side, the consequent stays the same. Okay, so that's, again, implication, or material implication, line 7. And then we simply apply double negation to get rid of this double negation here. Remember, double negation being a rule of replacement, even though this is really a subformula of the whole formula, which is a disjunction, we can apply double negation to get rid of the two negations, even though they're a subformula. So that's double negation on 8, and that is our goal. Okay, so, well, one thing that you might notice is if you did solve this proof or attempted it, there's more than one possible route to the goal, as we saw. And this is often the case when you are applying material implication or you have successive applications of modus ponens. That could be done as a hypothetical syllogism. So yeah, you often have a lot of sort of forks in the road when you're approaching the proof. There's no one correct way to do it, but you should find the way that seems most intuitive to you. So, and another takeaway from this is if you get stuck in a proof and you are dealing with either conjunction or a disjunction, just remember that you can translate from one form to the other using material implication. All right? Okay. All right, let's move on to another proof. Take a look at this one. I would begin by just entering the premises. Oops, and that's the conclusion. That's only one premise in this case. Okay, so what do we do here? What do we do with just a conditional? So remember, when you start looking at a proof, there should be certain rules that kind of pop out at you depending on what propositions you see. So with a conditional, I should be thinking whether I can apply modus ponens or possibly modus tollens or possibly hypothetical syllogism. So if I wanted to use hypothetical syllogism, I would need at least 2 conditional statements. Right? And similarly, if I wanted to apply modus ponens or modus tollens, I would need either the antecedent or the negation of the consequent on its own line. So what do I do with just a conditional statement on its own? All right, so in this proof, I'm going to actually illustrate 2 different approaches that are very different. So let's begin by picking up on what I was saying in the previous slide. I've got a conditional here. I don't know what to do with it, so let me see if it helps to turn it into a disjunction. Again, material implication on line 1 to get a disjunction. Okay, did that help? I don't know. Let me see. Well, I want to get t in the picture somehow. That doesn't exist in the premises. So if you have a propositional variable that occurs in the conclusion but not in the premises, addition is probably the way that it got in there. So what happens if I add t to this statement? So I have to put this in parentheses now. So that becomes 1/2. This statement becomes the left-hand side of a new disjunction, which has t on the right-hand side. And that's addition to line 2. All right. Now, what do I do going from here? So let me think ahead a little bit. How am I going to, what I want to do is get back to a conditional ultimately, right? So here I've translated the conditional into an equivalent disjunction. It seems like at some point I'm going to have to translate back from a disjunction into a conditional. So what would be the disjunction that would allow me to use material implication to derive this statement? Well, remember you take the negation of the antecedent and then the consequent on its own. So if I had this statement, then I could apply material implication to derive this statement. Well, what I have here looks really close to this, except the parentheses are in a different place. But that's fine, because these are 2 disjunction operators in a row, and when you have 2 of the same operator in a row, well, if it's conjunction or disjunction, then you can move the parentheses around. And the rule that allows us to do that is called associativity. Okay, and now we are in the situation that I was just talking about a moment ago, where we can just convert this back into a conditional. I'll be really explicit here. Let's just do it this way. H implies U or T. So again, that's applying material implication to line 4. So we take, I was being a little, you might add an extra step here, not H implies U or T. I guess if you want to be really explicit. and then we'd apply double negation to 5. So again, here we just take the negation of the left-hand side when you are applying implication, material implication. So if you want to be really explicit, then we include that step, and then we apply double negation to 5 to get H implies U or T as the conclusion. Okay, so this is definitely a good way to do it, but perhaps some of this might have been a little bit difficult for you. The repeated use of material implication, if you're not comfortable with that, might be a pain point. So there's actually another way that we can approach this proof, which I want to illustrate. So in the text, you read about conditional proof, and it's not going to work in every case, but there are some proofs that lend themselves really nicely to conditional proof. Okay, so conditional proof is where you add an additional assumption to the proof and then discharge that assumption later on after you've made some inferences. So let me illustrate. Here we start with the conditional. Now again, I said you can't do much with the conditional on its own. So if we had H, then we could maybe apply modus ponens and perhaps go from there. But we don't have H, so is there anything we can do? Well, I'm going to add it as an assumption. Okay, and this is a legitimate tactic for conditional proof. You add new propositions, which you don't have to justify, and they're called assumptions. And then if you want to actually prove your main conclusion, you have to at some point discharge the assumption. So let's say down here, line 8, I prove Z. So I assume H, then I apply some rules, and I get to Z. Then if I want to actually discharge this assumption, then I create a conditional. And I would say, I would indicate the line that has the assumption on it and the conclusion that I reached in that course of reasoning. And this tells me that if I assume H, then given the rest of the information, I can infer Z, right? If H, then Z. So I don't know H, so I don't get to infer Z, but I know that if I did assume H, then I would get all these other inferences and I would end up at Z. So that's how conditional proof works. You get to make up a new assumption, and then if it leads somewhere useful, you discharge it by inferring a conditional that takes that assumption as the antecedent and takes the result as the consequent. Okay, so let's do that here. Here I've added H as a new assumption. So what can I do? Well, obviously I can apply modus ponens to get U. Okay. So I've got U. Now I'm looking for something like U or T, so why don't I transform this into U or T using addition. Okay, now what do I do? Can I turn this directly into H implies U or T? Well, we don't have a rule that lets us do that directly, like introduce a new conditional from some statement, but remember that H didn't come from nowhere. It's something that we added in the course of our proof by assumption. So again, following that pattern that I just spoke about discharging the assumption, I take the line that bears the assumption, turn that into the antecedent, and then I take the result, let's say, that I reached, and discharge that in the consequent, and I annotate it like this. And now I have a very simple, perfectly legitimate proof of the same proposition. All right, so when you are trying to prove a conditional statement, conditional proof can be very useful because you can just assert the antecedent. And now I have new information that I can use in the rest of my proof. Right now I have H, and I can do things with H. Right, I can apply more rules using this. So I make a new assumption. then do some inferences, arrive at some result that I want for whatever reason, and then I discharge the assumption that I made initially by forming a new conditional, and I put the result as the consequent. And this is how that would be annotated. All right, so that's a perfectly valid proof. All right, let's take a look at a similar kind of example. The previous one, we had a conditional, and then in the consequent, we kind of have something like addition going on here. Here we have a conditional, and then it looks like something like simplification going on in the conclusion. So in case it wasn't obvious, again, from the previous example, the same thing would apply here. It looks like, W and D going to W, I could certainly apply simplification if I had W and D. W would be a good inference there, but simplification is a rule of implication, which means that it cannot be applied to subformulas. So I can't directly go from the premise here to the conclusion just by simplification, in case that wasn't obvious. Okay, so let's add the premise. Okay, so again, there's more than one way to approach this proof. Let me continue on the point about conditional proof to see how we might use that again here. So what we're trying to prove is a conditional. So if I wanted to use conditional proof, I would assume the antecedent. Let's put this here. Okay, so I begin by assuming the antecedent. Now, obviously, a reasonable next step would be to apply modus ponens. Okay, now I have W and D, and I could apply that is a whole formula where the main operator is a conjunction, so I can apply simplification to that to get just W. And now, again, I've made an assumption. I can't really conclude W because I assumed, when you assume new information in the course of the proof, then you can't just, when you reach some result, you can't really claim that that is the conclusion of the proof because you've added new information. Right? You can prove anything to be true if you're allowed to add new facts in the course of the proof or new information that doesn't even have to be justified. So if you actually want to use these techniques, whenever you assume some new information, you always have to discharge that in order to make the proof as a whole work. So I've assumed Q here, so I need to discharge that assumption, again, using conditional proof. So I start by assuming Q up here, then do a little bit of inference, get to W, and now I've shown that given this premise, if I add this assumption Q, right, if Q were added, then I could infer W. So that's just kind of the meta way of explaining what this rule is actually doing. Gonna run out of space probably. In any case, conditional proof on 2 and 4. Okay. All right, so hopefully the pattern is becoming clear here. Again, very useful for proving a statement that is a conditional. You always begin by assuming the antecedent because then you can discharge that assumption later on down the proof, perform some inferences, and produce the consequent, hopefully, of the thing you're trying to prove, and then discharge the assumption by creating a new conditional with the assumption as the antecedent and the so-called result, let's say, as the consequent. Okay, now I want to illustrate that, so here we've used conditional proof. There is another way to approach this, so let's just talk about how else we can handle this proof if we, say, didn't know about conditional proof or didn't know how to use it. Well, again, I'm starting with a a conditional on its own, so I can't really do much with this. So I'm kind of stuck right at the beginning, so I don't know what I'll do, so I'll just try again to apply material implication to convert it into a disjunction. Okay, did that really help? I don't know. I still feel kind of stuck, so what can I do here? I've got a disjunction and then a conjunction. Okay, so I still can't apply simplification because this is still a subformula. I can't say infer W and D because this is a disjunction. So what can I do? Well, remember that one rule that you can apply is distributing the disjunction across the conjunction. And the way you do that is you form a new conjunction which has each of these pairs of arguments as its conjuncts. In other words, I take not Q and W, not Q or W and not Q or D. So I kind of pair up the thing outside of the disjunction with each of the arguments inside. And what I end up with is not Q or W and not Q or D. Sorry, that's distribution 2. Okay, so again, you can distribute one operator across the other, and it has this kind of result. All right, so now I've got a conjunction statement, a complex statement that actually has a conjunction as its main operator. So I could apply simplification if I wanted to get not Q or W, and also I could get not Q or D. In the latter case, it doesn't seem like that's going to really help me because what I'm trying to reach is Q implies W. So let me just focus on the left-hand side. So first I apply simplification on 3 to just take out the left-hand side. Okay, now what do I do from here? Well, again, hopefully this is starting to become familiar. I have a disjunction here, and I'm trying to reach a conditional. So let me turn this disjunction into a conditional. So I take the negation of the left-hand side, and I leave the right-hand side as the consequent. And the rule is implication. Now I've got something that looks a lot like the formula that I'm trying to prove. Just need to get rid of those leading double negations. And there you go. So I just applied double negation to 5 to get rid of these negations and end up with 6, which is our goal. Okay, so this time, it's, again, neither proof is necessarily that much more complex or difficult than the other, but maybe one of them seems a bit more natural to you or not. So this one gives you another illustration of how you can translate a conditional to a disjunction and then back again, and this can allow you to apply the rules that are most applicable to disjunctions when you want a disjunction, and the rules that are applicable to conditionals when you have a conditional. So it's kind of the best of both worlds. All right, so let's just take a look at one more. Okay, here again, pardon me, actually this one, a little bit more information up here. Okay, so this is again maybe a deceptively simple proof. It's not necessarily the case that difficult proofs always have a lot of premises, and very complex statements. This is relatively simple. These are simple statements, relatively speaking, but is it obvious how you can derive this conclusion? Oh, pardon me. Okay, this is incorrectly transcribed. Okay, this is the correct notation. for this proof, pardon me. So actually 2 premises here, still relatively simple premises, and the conclusion again is pretty simple. So, okay, so let's take a moment to think about this. Again, I got 2 conditionals here, and there is a common element that they share. So maybe hypothetical syllogism would be a way to go with this proof. But in any case, let's just start by listing out the premises. Okay. All right. Now, as I said a moment ago, one thing we could do is exploit the fact that this is the same as this, and then use hypothetical syllogism to directly connect this statement and this statement. Okay. Now, what can I do from here? So how can I proceed from here? So I'm trying to prove I. And again, I have some conditionals, but I don't have anything to kind of, that's going to help me in actually discharging any of these assumptions or applying modus ponens or applying modus tollens. That's kind of how you get from a conditional, which doesn't really tell you how the world is, to a statement like I or some proposition that actually, bears content. So I don't have C or I or anything like that, which is going to help me apply modus ponens or modus tollens. So I'm not really sure how to proceed here. So one thing I want to point out is this is a very strange statement, right? C implies not C. That should strike you as a bit strange. How can, say, P imply not P? If P is true, well, in this case C, if C is true, then not C is false. So if this is true, then that's false, which seems to go against, the meaning of a conditional. So how's that going to work? Well, actually, what this shows you is that C must be false, and let me illustrate how that works. So again, I want to show you that material implication is a really, really powerful rule. Here I'm applying material implication to line 2 to take the negation of the antecedent or the consequent on its own. And now I have not C or not C. Okay, and that's kind of redundant, right? It's the same thing on the left side and on the right side. Okay, what can I do here? So one thing I can infer is not C, and the rule is tautology, line 4. Okay, so if I have P and P, or P, then I can apply tautology to derive simply P. And why is that the case? Right, because again, the left-hand side tells me that not C is the case. The right-hand side tells me not C might be the case. So depending on whichever alternative we choose, either way, not C is going to end up as true. So it should be obvious, that you can kind of reduce this disjunction when you have the same thing on both sides and just infer, that statement on its own. And we call that tautology. Okay, so now I've got not C. And what can I do with that? Well, again, let me look back at this for a second. Here I have a conditional with C as the consequent, and here I've inferred not C. So I can actually apply, that's correct. I can apply modus tollens to get the negation of the antecedent, right? Not I implies E. The rule there is modus tollens, lines 1 and 5. Okay. All right. Still not reached I. Now I have not. I implies E. Now, if you have a lot of practice with this, one thing you might pick up on is the fact that when you have the negation of a conditional, right, there's only one possible case that makes the negation of a conditional true. Right? The negation of a conditional is true just in case the antecedent is true and the consequent is false. Right? Because the negation of this conditional is going to be true when this conditional is false. And the conditional is false just in the case where I, the antecedent, is true and E, the consequent, is false. So if this whole thing is false, then I know ultimately that this has to be true, I has to be true, and E has to be false. So intuitively, that kind of reasoning hopefully makes sense. But we have to take a couple more steps before we actually get there. So what do we do? Again, first thing that we want to do is get rid of this conditional and turn it into a disjunction. Line 6. Okay, now I have the negation of a disjunction. So what do I do with that? Well, the rule that applies here is, again, a very useful one. This would be the case of De Morgan's laws. So when you apply De Morgan's laws, you sort of distribute the negation across each of the parts. So I get not I, but then you also have to sort of switch the operator. So if it's a disjunction, it becomes a conjunction, and if it's a conjunction, it becomes a disjunction. So here it's a disjunction, so it becomes a conjunction. So you take the negation of the left-hand side and the negation of the right-hand side. And that's De Morgan's law, line 7. And now, hopefully, the route to the solution is clear. We're trying to reach I, so we just simplify, whoops, to the left-hand side. And then we simply apply double negation to get to our goal. All right. So, yeah, as it turns out, it looks like, let's see, line 3 didn't turn out to be that useful in this case. So that's fine. We don't get points off for having too many lines in our proof as long as they're all valid. So I think, again, this is a good illustration of when you get stuck dealing with conditionals, turn it into a disjunction, see if that helps. In this case, we ended up in this weird kind of position where you have the same thing on the left-hand side and on the right-hand side. And then another tip is when you have the negation of a conditional, to keep in mind that ultimately what that means is that the conditional is false, which means that the antecedent must be true and the consequent must be false, because that's the only case where the conditional as a whole is going to be false. All right, so hopefully in this video you got some practice with some of the more advanced proof rules and also with conditional proof. So try to bear in mind the difference between rules of implication and rules of replacement. Remember that rules of implication, which are covered in the first set of rules that we discussed, can only be applied to entire formulas. So, for instance, simplification, you have to have the conjunction as the main operator. Rules of replacement, such as double negation, De Morgan's laws, these can be applied even to subformulas. Okay, so that's a very important distinction to bear in mind. Okay, so get some more practice with these kinds of rules, and hopefully you will get won't be so overwhelmed when you come across this on the exam.